Okay.
Okay, good afternoon everyone. Our speaker today is Yichao Zhang, if I pronounce that correctly. He's now a postdoc in Le Havre in France, and he got his PhD on computer application technology in the Department of Computer Science and Technology at the University in Shanghai in May 2012. But part of his PhD work was done during a stay of more than 1 year in the Department of Computer Science of the University College London. During this year he's been working on different aspects of complex networks, and I think he's going to review for us today a summary of his work on random diffusion of weighted networks. Thanks for coming, Yichao.
Thanks. All right, good afternoon, everybody. First, thanks for coming. And in this afternoon, please let me introduce a couple of our works about modeling and random diffusion of weighted networks. In our daily life, there are a large number of networks. Many of them are neither regular nor random. These networks are generated by various complex mechanisms, so people name it complex networks. Actually, we cannot live without complex networks. We're using internet every day. We are browsing and downloading information from the World Wide Web. There are also many biological networks in our bodies. There are also nodes in social networks. Although complex, these networks also have some similar behaviors. For example, the scale-free and the small world behavior. The scale-free behavior was firstly found in citation networks by Director Solar Price in 1965. In 1999, Albert Laszlo Barabasi successfully set up a model recreating the behavior. And from then on, this class of networks has a new name, scale-free networks. So the model is called the BA scale-free model. The small world behavior was first observed in the experimental report. The report was proposed by Milgram in 1967. In this report, he concludes that we need at least 3 intermediaries to contact anyone in the world. In 1998, Duncan J. Watts successfully set up a model recreating the feature. The model processing a short average path length and a relatively high clustering coefficient. I will discuss this definition in the later discussions. So this model is the well-known WS small world model. Okay, let's see what the networks really are. In the left panel, this is the visualization of the model, BA scale-free model. For the BA scale-free model, we set the model start with a triangle. At each time step, a new node will join this network. The new node will connect with 3 old nodes. As you see here, new nodes coming will connect with 3 old nodes. And each old node has a different probability to be chosen. The probability is directly proportional to its degree. So this is a preferential attachment. Okay. This is BA ScaleFree network. For the WS small world model, it starts with a regular graph. We said every node has 4 links. Each link has an identical probability 0.1 to be chosen. At each time step, the chosen links are rewind by reconnecting one end to a randomly picked one. So, because of these 2 pioneering models, complex networks attract much attention from various scientific communities in the past decade. Okay, after introducing the typical models, let us come back to our topics today. We have 5 topics today. The first topic. In this topic, we will discuss how to solve the clustering coefficient in a weighted network called BBV network. In the second topic, we're going to discuss traffic fluctuations in weighted networks. That is, the traffic is caused by a class of biased random diffusion. We will discuss the definition of this random diffusion in this topic in detail. The third topic, in this topic, we will introduce a weighted network model. The network generated by this model possesses a scale-free degree distribution. That's why we call this scale-free, and a small world model. So it also possesses the small world property. In the fourth topic, we will discuss the diffusion annihilation process in a class of weighted scale-free networks. We will show depletion zone and segregation in this class of scale-free networks. In the last topic, we'll put some words about the rumor evolution in social networks. Okay, that's the outline. Based on the empirical data of American airline networks, Alan Barrett, Mark Barthelemy, and Alessandro Vestigliani proposed the weighted network model in 2004. We called it the BBV model. The BBV model is the first successful weighted network model. It successfully represents the feature of the American airline network. To provide an analytical solution to the clustering coefficient of this model is a challenge. This model has 2 features. One is preferential attachment. That means when a new node N joins this network, the probability to connect with an old node I is directly proportional to the old node's strength. The other feature is co-evolution of weight and topology. That means when N joins this network, the weight of the new link equals W0. At the same time, the strength of node I will be changed as well. The increase of the strength equals W0 plus delta. And this delta will be distributed to these 5 links, these 5 old links. And correspondingly, these 5 nodes, their strength will be changed as well, because the strength is defined as the sum of the link weights around it. So that's the feature of a BBB network. So we're gonna solve the clustering coefficient in this model. But what is the clustering coefficient? The clustering coefficient denotes the thickness of the node. It's defined as the number of links between the node's ki neighbors over the maximum of the number. The maximum of the number equals ki times ki minus 1 over 2. So this is the definition of the clustering coefficient. In the previous study, people used to use the mean field approach to solve this parameter. But that was in unweighted networks. In the weighted networks, from the topological prospect, one can find out that the BBB networks are dissociative mixing. So what is the dissociative mixing? That means most nodes in this network with dissimilar degrees are connected. So associative mixing means most nodes with similar degree are connected. So one can imagine uncorrelated is the nodes in this network are half associative and half dissociative. In this study, we found a breakthrough. That is, the BBB networks are weighted degree uncorrelated. That is to say, the weighted average degree of the ith neighbor is a constant. Based on this condition, we found another probability. This is the probability is particular for the weighted network, particular for this BBB network. The probability of the existence of the link ij is directly proportional to the product of its two ends strength, Si times Sj. So based on this probability, we establish the ordinary differential equation for the clustering coefficient. And in this differential equation, Pix denotes the probability that node I has x links among its neighbors. And the delta Cix denotes the increase caused by the number x link. So one can solve this differential equation to get the general solution of this differential equation. As we know, if we want to get a complete solution of this differential equation, we have to have a particular solution of this differential equation.
Sorry. This OD, I mean, how do you define it? I mean,
How to define it? Sorry?
I mean, what? Could you come back to the previous slide?
Okay.
So C is.
C
What is capital C? It's the
clustering coefficient. Yes, we defined it in the previous slides here. That's the definition of CI.
What is delta CI? The delta, the next slide.
You mean here? This one?
Yeah.
Okay. Delta denotes the increase caused by the number x link. And number x link is between the ki neighbors. For example, in these neighbors, they have x minus 1 links at this moment. So at the next step, they will have, if they can have the number x link, the clustering coefficient will be changed. This change is caused by the number x link. So we put the increase here, and the probability times this increase, and sum them together, we can get the total cluster coefficient, the change on the cluster coefficient. So this is the way we establish this differential equation. Yeah, if you are interested in this equation, you can check the paper. I will list it in the slides.
What is the initial condition?
That's not in the particular.
Let me ask the question another way. Can you in general write for any arbitrary network a sort of equation of this form, that the clustering coefficient, the growth in time for the clustering coefficient can be written as an ordinary differential equation in this form?
Yes, you can do it.
You can do it for
all the networks, but
Okay,
you cannot get this.
Yeah, I understand. The probability will be different for different networks,
Yeah.
and you can always write it
So
in this closed form.
So if you without this, you cannot solve this.
Yeah.
So that's a problem.
So what the advantage of the BBV networks is that you can really write down the Pij in
Yes.
a code.
It is. Yes, it is.
Thank you.
Okay. So if you want to get the complete solution of this equation, we have to get a particular solution for this differential equation. So if you want to get to the particular solution, you have to borrow another definition of the clustering coefficient. That's the same parameter, but defined in another way. It equals the number of triangles centered on node I over the number of triples centered on node I. Triples here means node I plus its two neighbors. These three nodes are triple. And if there is one more link in this triple, that means one link between two neighbors, this triple will form a triangle. So the number of triangle over the number of triples is equivalent to the former definition. But because of this definition, we can get the approximate solution for the clustering coefficient when node join this network at that moment. When a new node joins this network, the moment is called Ti. For node I, that's the moment I join this network. We simply sum the probability that the triangles can exist around node I to get the numerator. So you can see three links. Probability is listed here. We time them together, we can get the probability of the existence of the triangle. So sum all the nodes together, one can get the sum of the probability. That is the sum of the probability of the triangles connected to I. And the number of the triples centered on I can be get by this expression.
So this equation for clustering coefficient, it assumes that the nodes ij and v, the probabilities of the connections are they are not correlated at all.
Yes, they are not correlated.
Okay, so basically for any network that has significant clustering coefficient, like for instance social networks, this won't work at all.
Yes, this is a particular for BBB network. So if for different, you can develop other definition of this probability and use the same way you can get this parameter. But the differential equation must be solvable. So okay. So
the definition, the triangles, are they allowed to overlap, that they share one common link, or have they be completely distinct? The triangles and
the triangle.
the definition of the clustering coefficient.
Yes. Sorry, can you repeat it?
Can they share a link, or have they to be disconnected completely? How do you count them?
Share link.
You can have two triangles with a common link in the middle, for instance.
These triangles only have one common node, I. only have one common node I. Yeah, probably they have shared link.
Okay.
Yeah, probably. If they have two nodes in this triangle are identical, of course they got a shared link. So that's definitely true. So one can get the approximate solution for this parameter. This is a particular solution for the ordinary differential equation, and combine the particular solution with a general solution, you can get the complete solution. So at last we compared the analytical solution as a red note here with the numerical result, black dots here. I have to say that's not a perfect match, but roughly you can see. This is okay. Let's move to the second topic. First, let's see two footage. It's already played. They show the traffic fluctuations in two traffic systems. One is a London bus, the other is a London tube system. So in the left panel, you can see the London bus. It's a little bit dark. As you see the sparkling points here, that's a bus. That's a bus. They are traveling around this city based on their schedule. I have to accelerate it because it's a really long one. We don't have time to go through it. And to the midnight, the traffic will disappear. So that's for London bus. And in the right panel, you can find out this is a visualization of London tube. I have to say, this is not done by me. This is done by my colleague Anil Bois. He just dropped his PhD study to open the company because he think this can make money for him. So this, I have to say, this is a lovely picture, footage. And for London tube, you can see there is a peak in the morning. Here you can see the peak, that's the traffic peak. So this is a very huge fluctuation. That's the morning rush hour. So I pressed the wrong button. And this is for the morning to the noon. It's just small traffic in the system. One can expect another peak in the afternoon around 5 p.m. So that is the traffic all day for one day. So one can find out that the traffic fluctuation in these two systems are dramatic. As is known, traffic fluctuation is the key reason for the traffic jam. To provide an analytical solution to the relation between the traffic and its fluctuation is a challenge, I have to say. So we built up a model. This is the definition of the model. This is a biased random diffusion model. In this model, the network are weighted. The link weight is defined as the link 2 n's degree, the product of 2 n's degree power theta. And theta here is a weight parameter. It controlled the heterogeneity between different links. And the node strength is defined as the sum of link weights around node I. At each time step, a worker will choose a link to go based on the link's weight. it is directly proportional to the link's weight, and inverse proportional to the strength of node I. So that's the definition of the random diffusion. This one can see that's a biased random diffusion. So we derived the analytical results for the relation between the traffic, average traffic, and its fluctuation. One can see the scale. The function is a polynomial, and the scale between the sigma and if is a value between 0.5 and 1. We also derive the result for the links. And I guess that this is the first time people can get the relation on links. On nodes, in previous study, people already derived the result, but the result is wrong. So,
could you remember what is delta and what is R?
The wrong answer is here, probably have a 3 or something. But I see that is wrong, but not seriously wrong, just with a minor error.
No, I mean, what is the meaning of delta and R?
Delta, okay, I'll explain that. Delta is the fluctuation between the different time window. The time window is defined in the, for example, 1 day is a time window. You check the traffic day by day. The 1 day is a length of the time window. And between different time window, the traffic is different. For example, Monday probably we have larger traffic, and Tuesday we have probably less. So this is the fluctuation on the traffic between the different time window. And R is the average traffic for a day for one time window. So this is the average traffic. This is the fluctuation on the average traffic. So that's.
And then what is the relationship with sigma? Sigma. So that this is fluctuation on what? I thought it was in traffic. So what is the difference between sigma and delta?
A sigma is the fluctuation on each node. That's not based on the time window. That's for a node. This one is the average traffic for the whole system. This is for a node. So this is different completely. All right, based on the second topic, we're trying to set up a network model which can efficiently control the traffic fluctuation. That's natural, because we have to solve the problem. When you see a problem, you have to find a way to solve it. So that's motivation. That's the motivation. Okay, in this work, we propose the model. On one hand, this model represents many topological properties of realistic networks. For example, we call it ScaleFree because ScaleFree is realistic, and small world also realistic. On the other hand, this model can control the traffic fluctuation efficiently. So let's see the construction of this model. We said this model starts with a triangle. This is a deterministic model. The construction is controlled by two parameters. One is M, the other is delta. As you see, the gray links in this figure denotes the link with weight 1. So this link has a weight 1. At the next step, we'll get the weight times M. We'll get 2, because 1 times 2 equals 2. We'll get 2 nodes on this link. Then you get 2. And at the same time, the link weight will be changed. The increase here equals M times delta times the link weight in the previous step. As we said, the previous step, the link weight equals 1. So this one, we can get the value is 2. So at this moment, the link weight of this link equals 3. 1 plus 2, 3. So that's the evolutionary process, the updating rule for this model. And this is the third step. The model evolves as a fractal, but this is not a fractal, so people call it pseudo-fractal. Okay, that's the model. In this model, we also provided analytical results for the traffic on nodes and its fluctuations. One can find out there's a common factor in these two variables here. 1 plus m delta plus m over 1 plus m delta plus 2m and power t. As you see, this vector decays with t, because this part smaller than 1. So when you get a large time, this variable will be close to 0. So this vector decays with time exponentially. If the total traffic R increased at a slower speed, this one is the total traffic, as we defined it in the previous topic. That slower speed means slower than the exponential factor. If this increased slower than this network can efficiently control the traffic, and its fluctuation. So we also gives out the result on the links. One can see a similar factor here, also smaller than 1. So the model can also control the traffic on links. So that's the model, and it seems we solved the problem. Okay. So for this model, we also provided analytical solutions for the accumulated degree, link weight, and the node strength distribution. In addition, we also analytically discussed the degree correlation and the average path length analytically discussed. So that's almost complete. All right, let's move to the fourth topic. This topic is about a random reaction. As a type of a diffusion reaction, diffusion annihilation is an interesting and important dynamic in networks. It is closely related to the epidemiology and the information dissemination. As we know, a lot of people doing research on the epidemiology and the information dissemination in networks. But this dynamic is closely related to this process. In the past 10 years, people do not believe there is a depletion zone and segregation in the ScaleFree networks, unless the network is a fractal. But in this work, we're going to show you something. We're going to show you that there is a depletion zone and segregation in the non-fractal ScaleFree networks. So that's really different. The construction of this model is controlled by one parameter here. When Q equals 1, the construction will be like this. This is step by step. When Q equals 0, the construction will be like this. So when Q equals a value between 0 and 1, that's going to be a combination of these two shapes with a certain probability. In this class of networks, one can find out the empty area here for the A plus A annihilation process. A plus A means identical particles can react with each other. One can find out for A plus A annihilation process, there is an empty area. This empty area is called a depletion zone. And the depletion zone in this network is actually caused by the dissociative mixing. We started this topic in the weighted network is to try to amplify the power of hops, because the power in the weighted network will be stronger than that in the unweighted networks. One can see here, as a worker, the worker is the random diffusion workers, the random workers, and the random diffusion process is just as what we talked in the second model. That's based on the link weight. That's a biased random diffusion. So based on that random diffusion, hops can attract the workers around it. So one can expect if a worker traveling around this hop, at next step the particle probably will get this side, and one step later it will be tracked back. It has a higher probability to be tracked back. So in this process, the particle will travel around this hub for a long time. And because of this attractiveness, the random diffusion, the rate of the random diffusion slows down. And so is to the rate of the diffusion annihilation process. Also, this attractiveness generates the depletion zone. This is for A plus A annihilation process, and that's the same in the A plus B annihilation process. A plus B annihilation process denotes only different particles can react with each other. If the identical particles collide with each other, nothing is going to happen. This is an A plus B annihilation process. So one can see in this network, it's not a fractal, but also we can see the diffusion zone and segregation. All right. Then we turn to the last topic. This is a cartoon about a word, telephone. The story starts from a conversation. I think it's a private conversation. And the guy probably get it from next door. They get just a piece of the information, just a part of them. And the guy get this information, also question this information. But the third guy heard this question, but just a part of this question. And the fourth guy changed the content because they cannot get it correctly. Maybe because of this woman between them. So, step by step, the content changed constantly. And to the public, they confirmed this question and spreading out the wrong information loudly. So that's the cartoon show you what is the rumor evolution in the social networks. This phenomenon also in some conditions called the Chinese whisper.
Go ahead, Yichao.
It's okay? Okay.
对对对。
Okay. So indeed, the rumor evolves constantly during its spreading process. In the early psychological experiment, researchers found 70% of the content will be lost in the first 6 month transmission. That means a lot of information actually be changed during the first few steps. So based on this observation, we proposed this model. I have to explain the original rumor model because that's the background information. In the original rumor model, each individual has 3 roles: ignorant, spreader, and stifler. The dynamics is like when the ignorant get a rumor from a spreader, the ignorant has a certain probability to become a spreader. But in our model, we set the probability 1 to simplify this process because we want to focus on the rumor evolutionary process, not the spreading process. That's different stuff. Sorry? That's spreading. Okay. So when 2 spreaders spread the rumor to each other, 2 of them will tend to be stifler. The stifler means it doesn't care about this message anymore. So if 2 spreaders spread the rumor to each other, they will tend to be stifler, both. And if a spreader spread the rumor to a stifler, the stifler will tend to be a stifler because they know his friends have no interest in this topic anymore. So that's the original rumor model. I have to see that makes sense. That makes sense. But in our model, we have, except these 2 dynamical roles, we have 2 strategies for each individual. These 2 strategies, one is to forward. We use square here to denote the forwarder. Circle here to denote the forwarder. When a forwarder receives a rumor, he will directly spread the rumor to its neighbors without any change. For example, you get an email, found it interesting, just forward it to your friends, and you don't see anything. Just look at this. That's forward. But as a modifier, we use square to represent the modifier. It probably will change a little bit, just like what we see in the cartoon. They probably will change the content to get shorter, concise, easy to grasp for its neighbors. For its neighbor just can get this information by 1 or 2 words. That's the best way. So in our model, we just divided the people into 2 groups. One group is a forwarder, or the other group is modifier. So this is an illustration of our model. The model enters this network from this forwarder. The black denotes the version 1. When this spreader, this is the forwarder, and they get the rumor, it tends to be a spreader. The spreader spread this rumor to its 2 neighbors. One is a modifier. So the modifier changes the version 1 to version 2. And the other one is a forwarder. So it accepts version 1. So next step, because this spreader spread the rumor to the other 2 spreaders. So both, all of them will tend to be stiflers. But at the same moment, this spreader holding the version 2 is spreading the rumor to its neighbor. This is another modifier. And simultaneously, this forwarder spread the version 1 to this neighbor. At this moment, the modifier only take the latest version, the version 2, and change it to the version 3. On the other hand, as a neighbor of this forwarder, this modifier gets the version 1 and change it to version 2. So we get version 3 and version 2 here. At the 4th step, as usual, these 2 will tend to be stiflers. And this forward And this modifier spread the rumor to its neighbor, another forwarder. So the forwarder get the version 3. Similarly, this modifier changed the version 2 to version 3. At the 5th step, these two individuals spread the rumor to the last individual here simultaneously. And because they hold the same version, version 3, the last individual gets the version 3 for sure. And at the last moment, everyone in this network tends to be Stifler. That's the whole process. That's the illustration of our model. So what's the conclusion of this model? The conclusion is simple. We just got one conclusion. The conclusion is, one can see in panel A, C, and D, here, this is a degree. This is the average revised frequency for the degree. So that means when an individual with a high degree, you can probably get a less revised rumor. That means the original rumor. So for A, C, D, this is scale-free network. This is a small word network. This is a random graph. We can, all of them, in all these panels, we can observe this phenomenon. So that means the people in the social network with a high connection, with high connectivity, they probably can get original rumor easier. So that's the one conclusion. We also derived the analytical solution for the global average revised frequency. This is really long stuff. For the small one network. So for this network, we got this variable analytically. And because in the panel B, we cannot provide the revised frequency for the regular graph. So we only show the global revised frequency for all the networks here. One can see that this looks like almost a linearly decay with the fraction of forwarders. So one can see that the slope for the regular graph is the highest one. So that's all the observation and conclusion in this model. All right, that's all. Thanks for your time.
Thank you, Zhang. Are there further questions or comments?
You use this BDD model, and is this the same as you apply to the tube and the bus fluctuations? I missed which kind of model. In the model for the fluctuation in the traffic, you also have some, the weight is some kind of product. Is the same as in the DB?
Yeah, we almost use the same definition on the link weights. That's the link, the weight equals the product of two ends, degree and the power theta. That one was first observed in the empirical work done by the BBV. They get the theta equals 0.5 in the American airline network. So we accept this concept to use it to the other.
So my question was so you use the same model. You try to fit again this exponent theta, and is the same exponent, or you try to refit to obtain it for the bus for the.
No, that's.
Do you use the same value as the traditional model?
That one is real data. We just did the model, so the visualization is based on real data, based on the real London bus system and the London tube system. That one is done by my colleague. So he is doing the real data, the large data, and the visualization on it. I just borrowed the footage to show my theory. So one can see the fluctuation inside is the main reason for traffic jam. because we experienced the traffic jam in the morning and at 5 p.m. So,
But you don't have to try to compare the results of your model with the empirical.
yeah, he didn't want to give me the data.
Okay.
That was your friend. More comments or questions? In your last, can you go back one, transparency? No, yeah, that one. Okay, this is simulation, right?
Yeah, this is simulation.
How large are these networks?
I set the size as 1024. Some people ask me why I set this as 1024. I said it's just because of my personal reason.
And I mean, there is, I guess, a crucial parameter, which is the ratio of different type of agents. And you didn't show us any result or anything on how results depend on the proportion that you have of the spreaders and. I mean, you have different types of agents. Ones that just spread and others that modify.
Yes.
How do these results depend on the proportion of?
In here, this is a result. This is a fraction of folders. So the larger we get more folders in the network. When the f equals 1, the whole network are full of folders. So one can see it's a really a long line.
So it's a continuous thing. There is no critical value of the number of modifiers.
No upper bound. No upper bound.
Okay, thanks. Any further question or comment? Well, if not, Yichao will be around this afternoon if anyone wants to talk to him. Thank you.